The Dijkstra algorithm is the foundation of linked state routing. It addresses the single source shortest path problem, which means it finds the minimum cost path from one node to all others in a network graph. The algorithm works for both directed and undirected graphs and follows a greedy approach. It always extends the path to the closest unvisited node. It assumes that all link weights are non-negative, which is true for most network metrics like delay or bandwidth cost. Each router uses this algorithm on a complete map of the network, built from information flooded by other routers. The output is a table of the shortest paths from that router to all destinations. This ensures efficient and loop-free forwarding decisions in real time. This example walks us through the Dijkstra algorithm in action, starting from node A. In the top right corner, we see the original graph with link weights. The algorithm builds the shortest path tree step by step, starting with only node A in the set M, which contains nodes whose shortest path has been finalized. In frame A, the closest neighbors B and F are evaluated. F is added first since its cost is 1, the smallest. In frame B, node B is added next with cost 1, and the tentative distances for C, E, and D are updated through B and F. By frame C, node F is already in M, and now node C is chosen as the next closest with cost 2. The process continues, always choosing the node in the remaining set V with the lowest cost. Dijkstra's greedy nature ensures we always extend along the most efficient link. By the final frame F, all nodes are included in M, and we have computed the shortest paths from A to every other node in the graph. This slide shows the step-by-step construction of the routing table for node A using the Dijkstra algorithm shown in the previous slide. We start on the left side with only A in the set M, so we know the cost to A is 0 and all other destinations are set to infinity. As we add more nodes to M, starting with B and F, we begin to calculate the shortest paths to other nodes. For example, once F is added, we can reach E through F with a total cost of 3. With each new iteration, we compare the costs of alternative paths and always choose the minimum. So, by the time we reach the column labeled A, B, C, D, E, F, all destinations are reachable from A with the shortest cost, and the table now includes the next hop information as well. For example, to reach D, we take the path through B. This routing table is what node A would use to forward packets efficiently through the network. We now focus on the comparison of distance vector and link state routing algorithms, focusing on their complexity and behavior. Bellman-Ford, which underlies the distance vector approach, has a complexity of O(n) per E, and in dense networks this can reach O(n) to the power of 3. On the other hand, Dijkstra's algorithm, which powers link state routing, has a complexity of O(n) to the power of 2, and is generally faster, especially when implemented efficiently. Both algorithms will reach the same optimal result under static conditions, but they behave very differently in dynamic scenarios. Distance vector converges more slowly and relies only on local neighbor information. Each node knows only what its neighbors tell it. Link state, however, requires a broader view of the network, which each node builds via flooding, making it more responsive, but also more resource intensive. So there's a trade-off: simplicity and locality with distance vector versus speed and global awareness with link state. To scale globally, the Internet is organized into multiple autonomous systems, or AS, and AS is a group of routers and subnetworks under a common administrative control, like a university, an ISP, or a corporation, typically running consistent routing policies internally. When it comes to routing protocols, we distinguish between two categories. Interior Gateway Protocols, IGPs, operate within a single AS and handle intra-domain routing. Examples include OSPF and RIP. On the other hand, Exterior Gateway Protocols, EGPs, manage routing between different AS. This is known as inter-domain routing, and the main example is BGP, which is the backbone of global internet routing. The diagram shows two AS, ASA, and ASB, with IGP used internally and BGP handling communication between them. This separation ensures scalability and administrative autonomy across the internet. A routing domain, or RD, refers to a portion of an autonomous system where a single consistent routing protocol is employed. Within each RD, routers exchange routing information using the same interior gateway protocol, such as OSPF or RIP. In the illustration, we see AS-A partitioned into three routing domains, RD1 and RD2, each run a different IGP, labeled IGP1 and IGP2, respectively. RD3 connects these domains and facilitates communication between them. This design allows protocol heterogeneity within the same AS, enabling administrators to deploy different routing protocols based on operational requirements, performance, or legacy constraints. Routers that sit on the boundary, like R4 in this example, must be capable of translating or redistributing routes between domains, ensuring consistent end-to-end reachability across the AS. Routing protocols are categorized into interior gateway protocols, IGPs, and exterior gateway protocols, EGPs, based on the scope of their operation. IGPs are used within a single autonomous system. Among them, RIP and IGRP follow the distance vector approach, where routing decisions are based on hop count or similar metrics, and routing information is exchanged periodically with neighbors. In contrast, ISIS and OSPF are link state protocols that build a complete view of the network topology and compute shortest paths using algorithms like Dijkstra. EGPs operate across autonomous systems. The most prominent example is BGP, the Border Gateway Protocol, which adopts the path vector approach. Unlike distance or link state protocols, BGP exchanges path information, including the list of ASS traversed, to ensure policy-based interdomain routing.